Hi everyone, so today we're going to go over statistical learning and some basic machine learning topics. These are like your core fundamental topics that are also covered in exam predictive analytics. These are just fundamental machine learning ideas. So first, supervised versus unsupervised learning. Supervised learning is the entire idea of training a model when you have a specific set of labeled data or target, you have a target variable. So this can be in credit card fraudulent detection. This could be if the transaction was fraudulent or not, or detecting if someone has a tumor or not, if they have a tumor or not. So it could be a binary variable, but it could also be like a continuous variable if you're predicting score, if you're predicting probability, if you're predicting revenue. All of those can be continuous or numerical variables, or this target variable could be binary or even categorical as well. But as long as you have a target variable, as long as you have labeled data of what you're trying to actually predict something, that's what supervised learning is, having this clear sense of what the target is. And so example, sort of an analogy in that is if you have sort of, in this case, when you have a library, you have structured layer where certain books are in each different section of the library, they're all labeled. And so when you have labeled data, when you have data that has a specific target variable of what you're trying to predict, then that's known as supervised learning. And the reason that this is very important is because sometimes we just have a task that we want to predict X, or we want to know Y, or we want to just classify if something is fraudulent or not. If we want to classify some like a tumor as benign or malignant. If we just have this classification or regression problem where we have a clear goal, we have a clear label, we have a clear target variable in mind of what we want to predict, and we have data for that, then that's what we consider supervised. It's learning from that target variable through gradient descent and all that. But that's supervised. We have a label, we have a target that we want to accurately predict. Unsupervised is the exact opposite of that. We don't have a necessary fixed target, or we don't have a label to our data. This, you can think of this data as sort of unstructured almost. You can think of it, especially during if we want to cluster different customers, we don't have a specific target variable we want to predict, but what we could possibly do is we could cluster these individual customers depending on their demographics. And so this obviously can help the marketing, et cetera, et cetera. But if we don't have a fixed target variable, if we don't have a fixed outcome that we want to predict, we're just trying to look for trends, trying to look for different clusters. We're trying to learn from the data itself, the patterns and the insights from the data itself. Then that's what unsupervised learning is. This is known, obviously, clustering algorithms, PCA, dimensionality reduction algorithms, hierarchical clustering, all these different clustering algorithms where we're finding insights from the data itself without a target variable or without any labeled data. That's the core difference. And then we also have sort of semi-supervised learning. We have like a hybrid of these two. We have self-supervised learning, but these are like the general, like the two core types of the learnings in machine learning. Unsupervised, where we have unstructured data, where we have uh, data that's not labeled, where we're clustering, finding insights within the data, and then supervised learning, where we have a target, we have a clear outcome, clear goal that we want to predict. And so now let's get into the concept of training versus validation versus testing. Your training data set is where your model is going to be fitted. It's going to be learning the parameters. So if you have a linear regression, it's going to be learning what the beta coefficients are. If you have logistic regression, likewise, it's going to be learning the parameters through gradient descent learning, whatever learning algorithm you have implemented. And it's learning, obviously, it's training on that data set. That's the data set that's used to fit the model, to create the model. So just as like an example, if a dog's training for an obstacle course, it's going to learn first. It's going to learn what the obstacle is, what are the different obstacles in the course itself. So that's what the training data helps the model to do, to really figure out the parameters in creating the model. Once we have a model created, and once we even have multiple models created, we really sometimes we want to get a better understanding of what model to use. And so this is where the validation data set comes in, where we're not testing the data, right? That comes later, but we're just seeing the usefulness of the data. We want to see which model do we actually want to use first. And so we can use that. We can use the validation data to actually figure out which model not performs, but which model we can actually use moving forward. And that's the validation state. There's a lot of there's a lot of difference or similarities between validation and testing, but it's really important that we make sort of the distinction between the two. Testing is independent, right? Testing is independent. Validation, you can think of it as selecting the model, evaluating the model usefulness. If we have multiple different models, how can we pick a model? Um, that's the validation data set. Testing data set is completely independent. We want to evaluate the performance of the model. So you can do this through root mean square or error or classification error. We have these other accuracy metrics, but the testing data set is really independent from training and even validation. We want to see how the model is able to perform on unseen new data. That's not in the training data set, wasn't in the validation. We want to see how it performs in real life per se. So that's the difference. These are the three sort of main categories of data sets. Then let's move into like sort of the structural form of certain machine learning models. So we have a systematic component to any model, and then we have sort of an error or random component. The systematic component is whenever we're measuring the relationships between variables, there's going to be a structured systematic component in which one variable influences another variable. Like if it's a quadratic relationship, if it's a linear relationship, if it's an exponential relationship, there's going to be some structure, there's going to be some systematic component to this entire relationship. Now, we know that it's not perfect. And that's where the entire error slash random component comes into play, is it's this extra noise. We know when we're trying to predict, let's say two different variables together, let's say it could be like GPA and like income or something. If we're trying to predict these two variables, yes, there could be some correlation. We can find some model to fit this data, but we know that it's not perfect. There's going to be outliers. There's going to be some noise in the data. There's going to be some random component where we won't be able to perfectly predict the target variable. And so the systematic component where we know that there is some relationship here, that's where the systematic component is. And the random component, you can think of that as sort of the error or the noise in the data that makes our prediction sort of not a perfect 100% of the time. And so in this, we have two different sets of different types of models. So we have parametric models and we have non-parametric models. Parametric models require the model to have some sort of functional form. So you can think of this as whenever we constrain something to constrain a model to be in a specified form. So if it's a linear regression and you only have, let's say, like two variables, we're constraining the model to be a linear model. If we have a quadratic, we're constraining the model to be in a quadratic form. If we have an exponential form of the model, we're constraining the model, we're limiting the model to be exponential in nature. So that's what we mean by parametric. It requires a functional form, and because it requires a functional form, it requires parameters to be estimated. So in the case of linear regression or logistic regression, we're estimating the betas. Same with exponential. But we have these parameters that we want the model to learn and to estimate. And again, it's a fixed functional form in the beginning that we provide, hey, this to the model, like, hey, this is the form that you're trying to fit to the data. Non-parametric models are exactly the opposite of that. We don't provide it a form, we don't provide it this functional representation of like what it should be. And so it really has the freedom to create its own nodes in the case of like or trees in the case of a random forest or decision trees. It has sort of the ability it's not constrained to follow this specified function that you provided. So there's different advantages and disadvantages to both. And so now let's get into the idea of flexibility, overfitting, underfitting, and the entire concept of bias variance trade-off. So this is obviously a very important concept in machine learning. We're always trying to create models that can not only really capture a lot of the trends and the patterns in the data accurately in the training data set, but also they can generalize well to new unseen data that it hasn't been trained on before. So that's the entire concept of overfitting, underfitting, and bias variance trade-off, is we want to achieve a balance between these two. So when we go to overfitting is the entire idea of fitting our model too closely to the data set. So for example, if we have this quadratic model, right? If we have a data set that follows this quadratic pattern and we fit a quadratic model to it, we add a squared term, we fit this model to it. But then we realize that sort of later on, it sort of doesn't follow that same pattern and it sort of generalizes to a linear sort of relationship. Well, then that would be considered we overfitting the training data set too closely, where we were trying to match the intricate patterns and the tendencies of the training data too closely and too specifically that when we go to unseen data that we haven't seen before in the training data set, then our model is not able to perform very well. And underfitting is the exact opposite of that, is when we fail, is when we overgeneralize to the model or to the data. We overgeneralize to the data. So we're not able to capture a lot of the systematic components. We're not able to capture a lot of the intricate patterns and relationships in our training data. And so this also leads, this also is not a very good thing to have because in the case of when it comes in the case of predictions, we're not going to even in overfitting and underfitting, we're not going to be able to predict well on the training on the testing data set. And so that's sort of this idea goes in touch with flexibility. So we have flexible models and inflexible models. So flexible models that allows the model to fit the data more closely. So if we have, let's say, a cubic function, right? And we allow the model to have a cubic term. We allow the model to be cubic, right? Then that's a pretty flexible model. We allow the model to fit the data to really fit the trends in the training data set itself. And so there's different advantages and disadvantages to having a flexible and even a non-flexible model. And so it really depends on really the data set you're working with, the business problem that you're trying to solve. And so as we talked about bias variance trade-off. So bias is an underfitting condition. We talked about when we are uh, overgeneralizing our training data set, when we're not really capturing a lot of the trends, we're not fitting the data very well. We're sort of just we're just generalizing, we're capturing the gist of the data, um, and it's overly general. Variance is an overfitting condition. When we have a high variance, we're highly overfitted to the data. We capture the training data set too closely. Our model fits the training data too closely, and it's when it does that, it fails to generalize to new unseen data. So obviously, there's a lot of trade-offs to this, and as we mentioned before, the entire idea of machine learning is we want to create these models that have a good balance of both. We're able to not just predict, not just really learn the nuances and intricacies and the patterns of the training data that we have, but we're also able to predict well on a new data that we haven't seen before. And so now let's say we've made the model. We've made our model and now we want to evaluate the model. Now there's obviously the first thing that comes up is just what's the accuracy of this if it's a classification problem or if it's a regression problem, what's the root mean square error. Let's take a look at classification. So typically that's what we look at. What's the accuracy of this? How many predictions can it get right? Positive on both the positive and the negative side. But where this actually becomes a problem is what if we have an imbalanced data set where we have, let's say, for example, we have 10,000 like credit card transactions, and we're trying to predict whether a transaction is fraudulent or not. Now, only really around like, let's say, two or three could be actually fraudulent in the entire data set. And so we have a really imbalanced data set. So if we predict all of the transactions to be not fraudulent, then we would have like a 99% accuracy. Is that a good thing? Probably not, because we've just predicted everything to be not fraudulent. Because there were only like two or three cases that were actually fraudulent. Our model like seems to be in terms of accuracy pretty good, but we realize that that's just not a good metric to evaluate the model on, especially when we have imbalanced data sets. So this is where we turn to other metrics such as precision, sensitivity, specificity, recall, false positive rate, things like that. And these allow us to really dive a bit deeper into the number of the false negatives, true positives, and really the entire confusion matrix. And of when we dive deeper into how many predictions were negative, how many of those were correct, that really allows us to capture how our model is performing, especially on unbalanced data sets. So if we look at sensitivity here, let me go back. So sensitivity slash recall. And the way that you can actually remember this is you can think of like sensitive as like in a positive way, or like you're recalling positive memories. So you can just a mnemonic for you to like actually remember this. But recalling, that's what the mnemonic I use is recalling positive memories, or like, or sensitive being like you're sensitive to like positive information or something like that. But just it's a good mnemonic. So it's percentage of the correct positive predictions. So obviously, you might have seen like a confusion matrix before, where you have like the negatives, and then you have the actuals versus the predicted, and then you have the positive, negative, positive, negative. And so sensitivity, recall the percentage of correct positive predictions. It it's from the entire pool of actual positive observations. And from the entire pool of actual positive observations, how many of those were correct? How many of those were true positives that you had predicted? And so the proportion of that is what we call the sensitivity. Specificity is the percentage of correct negative predictions. So how many negative predictions did you do that were correct? So out of the total actual number of negative observations, how many did you predict that were correct? And so which you might the question here becomes, which one do you use? Well, that depends on what problem you're actually solving. So in the case of, do we want to predict positive cases? If that's more important, then sensitivity or recall will be a better metric. If correctly predicting negative cases is more important, then specificity would be a better metric. So in the case of like fraudulent detection, or if we have imbalanced data, if we want to detect some fraud, and it's like only like 0.01% of the time where this is happening, you want to you want to have a better understanding of how it's able to correctly predict the negative cases, how it's able to actually predict the fraudulent cases, instead of just looking at the general overall accuracy of the model. And so this is where sensitivity and specificity can really help. And then false positive rate is one minus the specificity. So the specificity is out of the entire pool, of negative observations, out of the entire pool of negative actuals, right? The negative actuals. How many did we correctly predict that were actually negative? And the false positive rate is just one minus that. So how many false positives do we have? So false positives meaning that we have predicted them as positive, but that prediction is actually incorrect. So what's the percentage of that do we have out of all of the out of all of the truly negative observations? And let's see, precision, true positives over true positives plus false positives. So out of all of the positives, out of all of the positive predictions, what percentage did we get correct? So, right, so percentage positive predictions that are correct. So the pool in which you're working here is actually different. So for precision, the pool where you're gathering your true positives from is from the pool of all positive predictions. For sensitivity, you're pooling from all observations that are actually positive. So the true positives and the false negatives, right? Those are all of the actual positives. Precision, you're pulling from the pool of all of the positive predictions. Sensitivity, you're pulling from all of the positive observations, or all of the actual positives. Specificity, you're pulling from all of the actual negatives. So true negatives and false positives. So you really want to understand what pool you're getting what pool precision, sensitivity, and specificity actually comes from. And so now let's move on to linear regression. So this is a typical output of a linear regression model when you just fit like a couple of different variables. So you can see like the coefficients here. These represent how a 1 unit change in these predictor variables results in how that impacts the target variable. And then you have like residual standard error. I would just go through a high level, and then we have overview of this. So you have multiple R squared. So R squared is the entire idea of what's the proportion of the variance in the Y variable that our model is able to capture. So in this case, this model captures around 84% of the variance in the target variable, which is sepal length. And you can also do t-test on this, so you can see the value of the t-test. So in this case, for sepal length, the p-value is around 1.16 times 10 to the negative 14, which shows that this is the sepal length is a very significant predictor. And p-length is less than 0.05. That's typically the threshold, and that shows that that is also a very significant predictor in predicting sepal length. Now, well, we also have the hierarchical principle, which states that if you have interaction terms in your model, so if you have if you have an interaction term, then the individual terms also must be present in the model. So it doesn't really make sense to just have an interaction term, but then just not really have the other two variables in the model as well. So if you have an interaction variable, if you have two variables and their interaction, and you're considering their effect in the model, you also want to consider their individual effects first before you go to the interaction effect. So there's sort of a hierarchy to this that's covered in that principle. So yeah, that's just a general overview of machine learning on like just some stat concepts. Yeah, thank you very much, and I'll see you in the next video.